So in this video, I want to talk about a little bit more rigorous approach to looking at planetary gears. And I'm going to do so via something called the Willis equation. So suppose we start with a planetary gear, sun gear, and arm connecting the two as shown here. So I'm going to be using subscripts S, A, and P to stand for sun, arm, and planet as shown in this diagram. And if we think about the various ways in which this can move, right, there's several motions that are possible. The arm can rotate around its pivot point at the center of the sun. The planet can roll around the sun. And then, of course, the sun itself can turn as part of this motion. So to kind of put this all together, first we're going to consider only the rotation of the arm. So we're going to take this diagram and say we have let's start with our arm. And our arm has undergone some rotation, which we'll call theta sub A. And the sun is in the middle of this, of course. But we're going to keep the sun fixed and consider only the rotation of the arm at this point. And if we do that and we think about then what's happening with the planet, which is in here as well, then the rotation of the planet is the same rotation that we're getting from the arm. So the planet itself is rotating at the same rate because it's connected to the arm. Now, we're not at this point considering the fact that for this to be possible, the planet has to roll around the sun and be turning itself. So we're only considering a portion of the rotation. And therefore, I'm going to label this rotation theta sub p comma 1 to indicate that we're only considering a portion of that. So we have this rotation. Now, let's add in the roll of the planet. So again, the planet has to roll, or like a ball on a table, has to roll around the sun for this to be possible. So let's do a little drawing here again. Arm, sun, planet. And the rolling of the planet could be represented as an arced path. So let's call that S sub P. And as that planet rolls around the sun, the arm will also traverse a path. So I'm going to take a point on the arm at the intersection between the sun and the planet, and that will traverse a path that mirrors the arced path of the planetary gear. So we'll call that SA. And because these 2 points intersect, then by definition, SA and SP have to be the same. So those must be equal to each other. And we can rewrite this equation using the standard arc length equation, which is that S equals R theta. And therefore, we can relate these by saying that the diameter of the sun over 2, because I want R, and we're talking about this position at the outer radius of the sun, times the angle traversed by the arm must be equal to the diameter of the planet over 2 times theta p. Now I'm going to denote a number 2 here because we're only talking about the portion of the motion due to rolling. So again, we're only talking about a small portion or a piece of the rotation of the planet. So we don't want to kind of say that we're covering all of that just yet. But we get an equation that looks like this, and we can rearrange this equation to solve for the planet's motion. And we end up with ds by dp. So it's simply the ratio of those 2 gears to the motion of the arm. Now, we're going to take the last bit that we haven't considered, which is the rotation of the sun. And so again with our picture, arm, sun, and planet, now we're going to say that the sun itself undergoes some rotation, theta s. And so if the sun rotates clockwise, and we assume that the arm is held in place, then the planet has to rotate counterclockwise in order to balance that. So by the same notion that we had above, talking about the arc length positions, their arc measurements, s sub s, must equal s sub p. But, as I just said, if the sun rotates clockwise, then the planet has to rotate counterclockwise if the arm is held in place. So therefore, they have to be the inverse of each other, like this. So now we can rewrite that equation as minus ds over 2 theta s equals dp over 2, and the last portion of our planetary rotation. And so rearranging this equation for theta p3 gives us minus ds over dp theta s. So now we can put all this together and find the net rotation of the planet. And so we're just going to take and say that theta p, it must be equal to the summation of all the other, the three components that we've expressed now. So we get these three components that add up and allow us to relate the rotations of all of our gears. So let's go ahead and put that into a form that becomes a little bit more useful. And the rotations is fine, but we can also express this in terms of angular velocities. So we know that theta equals omega t. If we're talking about angular velocity, then multiplying that by time gives us angular position. And we can relate omega to the rotation in terms of like something like RPM, which might be a standard expression for the rotational speeds of gears. RPS, RPM, revolutions per second, for example. Multiplying by that by 2 pi gives us theta. So now we can plug all that in to our above equation, and we get something that looks like this. And what we see here is that all of these 2 pi terms are going to cancel, so we can cross all of those out. And we can represent the equation, the t's cross out as well. Those all cancel each other, so I'll cross those out as well. Now we can represent the equation as np equals. And if I take this and I'm going to multiply everything by the diameter of the planet, then I get an equation of the form that looks like this. And finally, I'm just going to collect my like terms here and get NP dP and now this gives me a new expression that relates the angular velocities and the diameters of the gears. So depending on what I know, I can plug different things into this equation and I can solve for the planetary gear, the arm, or the sun gear in relation to each other. In addition, because the diameters are related to the number of teeth on the gear, which is oftentimes what I might know if I purchase a gear, I could rewrite this whole thing in terms of the number of teeth on the gear rather than diameters. And it would be the same. My units don't really matter because I'm to solve for any of the speeds, I'm dividing diameter by diameter, so it's unitless in that way anyways. So whether I express it in terms of gear diameter or gear teeth doesn't really make any difference. So the last thing I want to add to this analysis is the existence of the ring gear. So I've got a new diagram on here, and I've added in the ring, poorly drawn as usual, but labeled it with a R, and I'll use subscript R for the ring gear components. Now, most planetary, or at least many planetary gear sets, will include a ring gear, so it's kind of important to consider how that factors into this sort of analysis. Now, to do this, I want to talk about this in a slightly different way. So suppose we have, again, angular rotation of the arm. So to do this analysis, I want to add in the velocity of the arm, and I'm going to pick this point here and say that the arm has a velocity v sub a. And now if I want to relate the velocities of other points, I can, for example, say, well, the velocity of the sun gear at its outer diameter right here is v sub s, and the velocity of the ring gear at its intersection with the planetary gear here is v sub r. And now I can think about how these things kind of work together. One of the things that I would see is that, well, the planetary gear, if I think about its velocity at this point, it's not going to be equal to v sub r necessarily because the planetary gear itself is moving. So therefore, v sub r is going to be equal to the summation of the arm velocity and the planet's velocity at that same point. And similarly, v sub s, I'll bring this out here for more room to write, is going to be equal to the velocity of the arm minus the velocity of the planet gear, because the planetary gear is rotating and in the opposite direction of the sun gear. And so therefore, those two things are related and depend on what the arm is doing. Okay, so with that, I now have some expressions I'm going to rearrange a little bit. So the velocity of the planet is the velocity of the ring minus the velocity of the arm, and the velocity of the arm is the velocity of the sun plus the velocity of the planet. And putting these things together, I can get 2vp equals vr minus vs, or vp is vr over 2 minus vs over 2. And now using some of our substitutions that we already used, we have v equals r omega, which is d over 2 omega, and omega equals 2 pi n. We can write that v equals pi d n. And if I take that and do some substitution down here, what I get is pi dp np equals all the same terms substituted in. And I see right away that my pi terms all cancel, and therefore I have np dp is nr dr by 2 minus ns ds by 2. So this expression now gives us NP-dP in terms of NR, DR, and NS-DS. And this NP-dP is the same as the NP-dP I solved for above. So I'm going to go ahead and substitute it into that equation. So if I take this expression and substitute it into that equation, then I get a big long one that looks like this. And with a little rearranging, and finally I'm going to take some geometry and substitute it in here. And that basically is that the diameter of the ring gear is equal to the diameter of the sun plus 2 diameters of the planet. Just that's the only way it works, right? Is for those diameters to be related in that way. So I'm going to take that expression and rearrange it to solve for dP. And then I'm going to substitute this into this equation. And what that does for me is gives me a new equation that looks like this. And so this expression, you can see now, doesn't have any terms related to the planet in it. And it gives me the ability to solve for what's happening with the ring gear if I know what's going on with the sun and the arm. So now between these two boxed equations, I have relationships with the planet in terms of the arm and the sun, and for the ring in terms of the arm and the sun. So this doesn't disagree with the way I presented this before in the matrix form. It's just another way to represent these relationships and kind of see how these various things work together. All right, thanks.